you, Giovanni, so much. Thank you for organizing this beautiful set of talks. And yeah, thank you for the invitation. It's really a great pleasure. As you mentioned, today I'm going to be talking about new effects in 3D magnetic nanostructures with complex geometries. I come from the Institute of Nanoscience and Materials of Aragon, from the Spanish National Research Council and the University of Zaragoza. But I was previously for quite a few years in the UK at the University of Glasgow and the University of Cambridge, where a lot of the work that I will present today was performed. The main, let's say, area of the talk, which is a bit changing a bit the topic with respect to the previous one, and I think it will be a good introduction as well for the one that Kailu will give after me, is three-dimensional nanomagnetism. So this is an emerging area of research within magnetism and spintronics, where we are investigating the possibility to move from the 2D world of nanomagnetism, where we have systems that are typically patterned with standard lithography methods and using also thin film deposition techniques, and that exploit the shape of the structure and typically the functional interfaces, as we saw in the previous talk with beautiful examples, and where the magnetization is confined to the plane, and therefore the functionality of these devices is confined to the plane, to a new area of research that is trying to investigate three-dimensional magnetic nanostructures that schematically are shown in this picture. So this leap from 2D to 3D is something common in nanotechnology, and is something that naturally comes from the great control that has been achieved over the last decades on 2D systems. And now we are pushing research to see if we can get the same type of control in 3D nanostructures. This is very challenging in many fields, and magnetism is not an exception, because we need new ways to fabricate these systems that get the same type of control that we had in 2D. Typically, we can think in terms of magnetic characteristic lengths that are of the order of tens of nanometers. So we need to be able to pattern our materials with the same level of control. We will also need to develop new characterization and computational tools, or adapt the ones that we have in order to accommodate for these new types of geometries. There are great opportunities in terms of the new applications that could emerge by moving into 3D. And also from a fundamental point of view, there are a lot of new physics and new science to investigate in 3D geometries. So the key point in all cases is that the magnetization, it doesn't need to be really fancy geometries. The magnetization will not be confined to the plane anymore. It will be in general across the whole volume, and therefore the functionality will be across the whole volume as well. But today I'm going to focus on interesting geometrical effects that we have been investigating over the last years. Before starting with the main purpose of the talk, which is showing you our results, let me motivate it a bit further to be more specific about what type of applications we can get if we move into 3D. The first one that comes to our mind is the vertical racetrack memory that was proposed by Stuart Parkin at IBM at that time several years ago, where we would have functional nanowires, where we would be moving spin textures such as domain walls with pulses of current, and we could have ultra high density storage and memory devices. Another example that is important as well is the one that was proposed by Russell Coburn. I was working during his ERC for several years, where he proposed to extend the functionality of magnetic random access memories vertically by introducing a lot of layers where we would have coupling in between, where we could exploit solitons. Finally, in the emerging field of neuromorphic spintronics, you can think that we need of the order of 10,000 synapses per neuron if we want to mimic the functionalities of the brain. So we are going to need a lot of interconnectors, and that cannot be done with 2D systems, so we need to go into 3D. So these are three examples of how exciting the applications could be in terms of 3D nanomagnetism for spintronics. In terms of physics, also let me give you a bit of a flavor. This is not a comprehensive summary, but you can think that because we move from something that is planar to something that is 3D, we are going to end up getting new types of spin textures, such as block point domain walls, or even Hopfians, which is the generalization of skyrmions, but into the whole volume, into the whole space. We can exploit complex topological objects such as a Mobius strip or curvature effects in order to induce new effects such as new ground states or new types of geometrical chiral interactions. And it's also quite interesting to look at not only the static effects, but also the dynamics, where we can get effects such as the spin-Cherenkov effect, where we have ultra high velocity for domain walls and spontaneous emission of coherent spin waves because of that. So many of these things are proposals. They have been developed by using micromagnetic simulations, other types of simulations, also theory. But we start, thanks to advances in experiments, to study these type of systems in the lab. And what I'm going to show you today is our work in this realm. So I will show you first how we fabricate our nanostructures using a quite particular and very interesting 3D printing nanoscale method. And then I will show you two effects. I don't have too much time today. I invite you to look at our website if you want to learn more about our activities. But today I will focus on the geometrical control of magnetic chirality that we can get, where we can imprint chiral spin textures and topological defects exploiting 3D geometrical effects. And also the possibility to, using again geometrical effects, generate free space topological magnetic fields. Okay, so let me briefly show you how we fabricate our nanostructures, because this is key for the rest of the talk. So we use this technique called focused electron beam induced deposition, or FEBID for short, which is this technique where we use a scanning electron microscope system with a pattern generator, where the beam is scanned like we would do to make an image, but we also insert by this gas injector system a gas that is absorbed on the surface and that we can decompose locally with the focused beam of electrons. So where the beam is scanned, where it is placed, some bonds of those molecules get broken and we get a local deposit. So it is a local chemical vapor deposition, this technique, induced by a focused beam of electrons in the kilo electron volt range. And as I'm going to show you now, is a unique tool for 3D nanoprototyping, because it is a one-step lithography process. So we don't need either resist or templates in order to generate, to fabricate some nanostructures. It's very flexible because it can be grown on almost any substrate. It has a great performance for 3D nanofabrication, because if instead of being scanning quickly, we stay for some time in the same spot, the beam, the deposit starts to go into 3 dimensions in the vertical direction. It has a nano-patterning resolution. This is a comparison of FEBID and its sister technique, focused ion beam induced deposition, with other additive manufacturing techniques that are being explored. And you can see how it is the one that has a better resolution, although it is slow. So we cannot fabricate large scale systems, but it is, as I was saying before, ideal for nanoprototyping. And finally, the fact that we can use molecules that directly have ferromagnets like cobalt, iron, or a mixture of both, allows us to directly fabricate ferromagnetic materials at room temperature, as it has been shown for quite a few years. If you are more interested in the fabrication of magnetic materials by FEBID, this is a recent review that we wrote with other colleagues. Okay, so the idea that we had a few years ago was to create a new framework for nanoscale 3D printing by FEBID. This was work done by my student Lucas Courage in Cambridge, and we are using the same approach as a standard 3D printer. So we break our complex geometry in 3 dimensions, layer by layer, and for each layer we need to calculate how much time the beam needs to be positioned in order to fabricate this particular layer. Yeah, so for that, we need to take into account the growth rate of the beam, and we will need to calculate how much is the time that needs to be there. And we also need to take into account the proximity effects that we have within a layer, an effect similar to electron beam lithography, that we have also these proximity effects of the electron beam with the material. So for that, we develop a rigorous approach that is based on the FEBID continuum model. I won't get into a lot of details. You have all of them in this publication. But basically, the FEBID continuum model is a very good way to describe what are the competing interactions present in FEBID. FEBID is a quite complex nanolithography technique. It has phenomena such as adsorption, dissociation, diffusion, and desorption, and all of them can be characterized by these characteristic frequencies that I'm including here. So what we did in this publication is, under particular conditions, we can find how much is the growth rate as a function of these frequencies, and then developing a simple calibration procedure, we managed to develop this new framework for 3D printing that I'm telling you. So this is a snapshot of our software where we have imported already a 3D object, in this case, this double curved nanostructure, which has been created by any standard software that you can think that you use for CAD, like AutoCAD or FreeCAD or Inventor or whatever. Okay, so what our program does is it imports this 3D design as an STL file, as a normal 3D printer would do. Then it slices our object, calculating how much is the height for each of the layers, as I was telling you before. And then using this FEBID continuum model, it calculates the dwell time, the time that is going to be, the beam is going to be on each of the spots in order to fabricate this 3D nanostructure, taking into account several effects. In particular, in this case, we were taking into account that the structure is going to get hot as it grows higher due to the electron beam and the low thermal conductivity of the material that we were growing in this case, which was a mixture of carbon and platinum. So you can see this is an SEM image of this 3D nanostructure, and you can see that the agreement is really nice. And this is what we have been testing for a range of 3D complex geometries, including this one, which have features down to hundreds of nanometers. We have done it for two precursors, this very standard platinum carbon, which is non-magnetic, but also for this cobalt-based precursor, and in 5 different microscopes, and the algorithm works really well. And just to finish with this part, let me show you some nice examples of 3D printing of nanostructures, like these nanocubes with 100 nanometer resolution that grow in a few seconds. We can also grow quite complex topological objects, such as a Mobius strip, that this is the CAD design at multiple angles, and this is the nano Mobius strip that we have developed. This is a cobalt Mobius strip that has been imaged at multiple angles to see that we got a good agreement with the CAD design. And we have even attempted to do some volumetric growth, where we have used this design of a nano hand, and we have realized it. So the features that this hand has have been well reproduced, but you can see that there is not a perfect agreement, because in this case, we would have needed to take into account all the interaction volume across the whole volume and not only in one layer. And this is something that we are now working on. But the message here is that we have a unique tool now in order to study new effects in complex 3D geometries. And this is what we have been doing, and I'm going to show you today 2 examples. And as I said before, the first one is on the possibility to control magnetic chirality only exploiting geometrical effects. So just as a brief reminder, what is chirality? Chirality refers to this property that, for example, our hands have, which is that the object and its mirror image cannot be superimposed to each other. Yeah, and this is a property that is omnipresent in nature. For example, you can find it in DNA or in some molecules, and the chirality is essential to provide properties such as the flavor, toxicity, or drug efficiency of these molecules. What happens with magnetism? Well, we can also have chiral magnetism. In general, magnetic textures are not chiral. So that means that the way spins evolve from, for example, up to down, there's no preference for that rotation to be clockwise or counterclockwise, because they are degenerate in energy. But we know that in some cases, when we have the combination of symmetry breaking and high spin orbit coupling, we have the emergence of an antisymmetric exchange interaction, which is called Jaroszynski-Morilla, or DMI. This is the Hamiltonian that describes this new interaction that tells me basically that, for example, the clockwise transfer of a spin, the spin would rotate more preferably in terms of energy clockwise than counterclockwise, for instance. And this happens in particular bulk materials that are non-heterosymmetric, like these B20 materials. And also in spintronics, they are realized by these asymmetric stacks of multilayers where the symmetry is broken because they are asymmetric, and we typically have a source of spin orbit interaction, for instance, via a heavy metal such as platinum. So, okay, this is the traditional way to create a chiral magnetic structures. The question is this really interesting for spintronics? And of course it is. So for that, I have taken the evolution that racetrack memories have had in terms of materials. And you can see how it evolved from something that was, the materials were not chiral like permalloy, to materials where we had chiral interactions by adding the platinum interfaces, and where we have then in that case chiral domain walls that can be moved at lower energies, or the new generations where we have even more fancy spin textures such as skyrmions that are topologically protected, and that allows to reduce again the interaction and the energy that drives these devices with the type of mechanisms that are used, for example, spin Hall effect needing to have this chiral interaction. So the message is chiral magnetism is really essential for modern spintronics, and not only thinking about racetrack memories, but there is a huge range of new chiral spin textures that I have made here a short summary that is not comprehensive, but you can see what a zoology of new chiral spin textures are emerging because of their potential for future spintronic devices. Okay, so you know that then we have this possibility to, for example, create these chiral magnetic systems by interfacing ferromagnets with other materials and create chiral interfaces. But as I show you, we have this unique possibility now to fabricate very complex 3D geometries. And the thing that we thought is, okay, let's look at nature and let's look how nature creates chiral systems. And typically it is done by helical geometries. DNA is a perfect example where we have the two strands that encode the genetic information. And we also have it, for instance, in plants, where we have really interesting effects, such as the inversion of geometrical chirality from left-handed to right-handed via this topological defect that in biology they call tendril perversion. So this is, for example, something that would be really difficult to realize in bulk materials or using interfaces in spintronic multilayer systems. And this is something that we could target with our new approach. And this is what we have been testing. This was a work led by Dedalo in Cambridge with strong support from Aurelio and Claire, where what we were doing is fabricating these double helix magnetic nanostructures using this cobalt octacarbonyl precursor that I showed you before that directly fabricates ferromagnetic cobalt. So the idea here is to have two strongly interacting nanowires that are going to be interacting both by magnetostatics and by exchange, because they are going to be fully overlapping. Yeah, so the materials, the two strands are connected. And then we are going to provide geometrical chirality by making them in a helical fashion. And this is a colored SEM image of the type of nanostructure that we are able to fabricate. There, it is colored in order to help you to see the two strands. So you see that the bottom part has been drawn as two strands that are left-handed. The top part is right-handed, and in the middle we have a tendril perversion, but at the nanoscale, as I showed you before for the plant. You can see in this TM image, as well as in the SEM image, the great control that we have over the geometry and the type of dimensions that we achieve for such systems using this new framework for 3D printing by FEBID that I showed you in previous slides. Okay, so we went to Alba synchrotron in Barcelona to image the magnetism of these nanostructures. So in Alba, there is a full field of view transmission X-ray microscope that allows us to get magnetic imaging by sending X-rays circularly polarized, both left and right. We can exploit XMCD in order to get magnetic information of what is the magnetic state of this system. And these are some selection of the results that we got. You have all the details in this publication for the as grown state. So this is the magnetic state that we get with the system as it was grown, where you can see that we have an alternating red and blue contrast in terms of XMCD for both left hand and right hand parts of the helix, with periodicity that is double the geometrical periodicity of the system. So if we do complementary simulations using μmax3 and we calculate the XMCD signal that we should get, what we find is that the XMCD signal that we are obtaining corresponds to having the two strands anti-parallel to each other magnetically. So left-handed, let me show you here, bigger, there will be one of the strands that will be going down and the other one is going up. And because the two strands are overlapping to each other, there must be a domain wall in between. In particular, our simulations show how this domain wall is of block character. This makes sense to minimize magnetostatic interactions in such a system. And the important thing is that the domain wall is chiral, magnetically chiral, and the chirality is defined by the geometrical chirality. So if we have a left-handed geometry, we will have a left-handed block domain wall. And if it is right-handed, we will have a right-handed domain wall. And this is one of the main goals of, or main achievements of this work, where we are controlling the magnetic chirality only with geometry and creating, therefore, chiral spin textures that are relatively complex, such as these domain walls. Okay, so another thing that you could think is, this is really interesting for the parts that have a well-defined chirality, left-handed or right-handed, at bottom and the top. But what happens at the tendril perversion, which is particularly interesting because it's this interface where we have the opposite chiralities. We have the interface in between the two chiralities. Okay, so for that, we were imaging the system at multiple angles, exploiting a stage that can do that, and measuring the XMCD at multiple projections. This is the electronic contrast, and this is the magnetic contrast. The tendril perversion is marked with an asterisk, and you can see how the XMCD at the perversion is evolving in a way that matches really well our simulations. So we have a really good agreement, and the question is what it is happening then at the perversion. Okay, so for that, what we can do in the simulations is unwind the magnetization state. So this is the micromagnetic simulations, and then we have we are unwinding the magnetic state in order to visualize it better. First of all, let's look at the parts before getting into the perversion, where there is a good chirality. So you see that we have a left-handed block wall here, a right-handed block wall here, and in the middle we stabilize a 3D vortex. The 3D vortex has okay, so this is what it is happening. At the tendril perversion, we have this 3D vortex that we can visualize nicely by performing in our micromagnetic simulations this calculation of the magnetic helicity. Here we are only showing the domain wall and the part of the vortex, where you can see that the vortex is also left-handed. And importantly, at the interface between the left-handed and the right-handed chirality, we have this null defect. So the important thing here that we are seeing is that we don't have a well-defined chirality here because we have this topological null defect that is necessary in order to interface these two types of chiralities. You can think about it analogously to what happens with these crystals with opposite chirality when we have block walls and null lines appear because of this different chirality. What happens here is that we are designing this 3D nanostructure in purpose in order to get this particular configuration with this topological defect at this position. Okay, I don't know how much time I have. I hope that a little bit more because I haven't had time to talk about the third topic. How much time do you have, Giovanni?
2 minutes, no more than 2 minutes.
Okay, so very briefly, I will show you that we have then extended our work on double helices, but in this case, the helices are not fully overlapped, and we have fabricated it the same way as before and measured it in a synchrotron, in this case at the Swiss light source, where we have done tomographic experiments. We have imaged the magnetic states at multiple projections, and then basically by exploiting these tomographic capabilities that Claire Donnelly has developed, we can reconstruct the magnetization of the system. as I don't have too much time, the important message that I want to tell you is that we can not only create, by using this approach, magnetic textures within the magnetic material, but we can also have stray fields in between these two strands that have topological features. So in fact, we have something that looks like a vortex for the magnetic state and an anti-vortex in the free space. Yeah. So this way of patterning complex double helices, in this case, is allowing us to basically tune the B field, not thinking only about the M field, but the B field in the whole space, including both magnetization within the material and a stray field outside the material, and have complex topological features in the whole space. I don't have time, unfortunately, sorry for having extended so much at the beginning, but you can get all the information in this paper that was published at the end of last year. And with this, I would like to thank a lot of people at the University of Cambridge, Glasgow, and in Zaragoza, all our collaborators and our funding sources. And I will just leave you with the conclusions and the outlook. And if you are interested in knowing more, visit my website, and we have some funding that could be interesting for you. Thank you very much.